Now we're going to do a demonstration of gain-based lookup table pre-distortion simulations using Java-DSP. We're going to start by using our long signal generator block, an input which is an OFDM modulated signal, 64 subcarriers, BPSK on each subcarrier, 4x oversampled. And after we take that signal and generate it, we're going to connect it to a power amplifier linearized by gain-based lookup table, which is the PA by LUT block. So we're going to connect the output of that signal generator to the PA linearized by lookup table, and then we're going to take the two outputs of the PA linearized by lookup table and connect them to a plot 2 block. Now if we look at this plot 2 block, what it's going to give us here, if we change our scale to dB, take mag squared so we're plotting power, and then let's make a grid to make it a little easier to see. What we're going to see here is the top plot is actually going to be the frequency output of the power amplifier without linearization, and the bottom plot is the frequency output of the power amplifier with linearization applied. So now if we open up our PA by lookup table block, inside this block we're going to see a whole lot of different things that we can tweak, and that shows us what's going on. So the first three things we can tweak are the lookup table size, or the number of bins into which amplifier input points are detected. The mu factor is our learning factor. If we make this factor big, we can learn what the gain correction factor is a lot faster, but we risk, in the presence of noise, learning it incorrectly. If we set the learning factor slower, it may take longer to learn, but it's going to learn the proper value. And the last factor here is the amount of power back off, or how far removed we are from the peak power of the amplifier. Next, what we'll see is a number of plots here. The first plot tells us what the correction factor is within each lookup table bin. So the horizontal axis here is the lookup table bin index, and then our gain factor, or the amount of gain applied to the signal, is here. And in this case, because the gain factors can be complex, here we're dealing with amplitudes only on the plot. Second is the quantity of points within each given bin. So this gives us kind of a distribution of where the amplitude is in our signal. So this goes back to our discussion of dynamic range. Next, we have the nominal PA gain at the center of each lookup table bin. And what we can see here is that because the amplifier is compressive, or essentially as the amplitude output which we desire becomes high, the gain gets reduced. We see that these points are actually below 1, whereas at the very lower powers, the amplifier gain is pretty much near its nominal normalized value of 1. Finally, this next table here shows us the amplifier nominal gains, which are in blue, the pre-distorted gains, which are in magenta, and then the combined gain at the center of each lookup table bin. So the linearized gain is in black, and that shows you, with the correction, what your gain is. And ideally, because we've normalized the amplifier, you'd want that gain to be 1. The fifth dialog here is actually very similar to that one, except what we are doing is, instead of just looking at the center of each bin, we're plotting it across the whole range of valid inputs to the amplifier. So if you have a very small number of lookup table bins, what you'd see is a lot of segmentation here. And this is gone through in the tutorial paper that runs you through many different scenarios. Secondly, here, similar plot, except now we're plotting magnitude instead of gain. So here what you should see is a perfect continuous line with a slope of 1. What we see is, before the pre-distorters really learned what's going on, we see that we have more of a compressive characteristic at the high amplitudes. And finally, the last two plots here is the adjacent channel power ratio in dB for nominal or non-linearized data, and in magenta for linearized data, versus the number of frames. And what we should see is, if our pre-distortion is working well, that the more data we pass through, the more we're going to learn about what the correction factors need to be, and this should improve with time, or index. Similarly, we have the error vector magnitude and a real similar plot for that, where we should be getting better across multiple frames, and depending on the learning factor we use is going to affect how quickly we learn, so how big that divergence is between the nominal and linearized. So if we play data through the system here, we should start to see the PA linearized gains start to approach 1 here, and we should see our ACPR and our EVMs improve across multiple frames.